Okay, so I'll skip this more general discussion of how endpoint functions of these boundary operators can be used to extract n-particle scattering amplitudes in flat space-time. Okay, so there is a way. Let me just state that. Okay, there is a well-defined. There's an equation that tells you that from these endpoint functions of boundary operators, okay, you can take this limit when all the delta i's go to infinity and do some integral transform to get scattering amplitudes. Okay, so scattering amplitudes of n particles in flat space-time where the external particles have mass mi, like say m1, m2, where these masses of the external particles are related to the dimensions of these operators by this formula here. Okay, so this is something I don't have time. I can discuss in the afternoon, or someone is interested. So, in particular, let me just see what I want to say. Yeah. So, in particular, I can study a 3-particle amplitude. Okay. So, for example, imagine that you want to study a cubic coupling between 3 particles, 3 scalar particles in flat space-time. Okay. Let me call that G1, 2, 3. So, the statement is that if you know the OP coefficient, lambda 1, 2, 3, between the corresponding operators, O1, O2, O3, then there is an explicit formula you can write, and it's actually very well known in ADS-CFT, this formula. So basically what you have to do to get this formula is just compute this Witten diagram. So you compute you take ADS, so the interior of this circle is ADS. You put your local coupling G1, 2, 3, okay, and you connect it with both two boundary propagators to your operators O1, O2, O3. That gives you a 3-point function by doing these integrals in ADS, okay, and this integral can be done explicitly. I'm not writing here; it's a long expression, but it's some known function, ratios of gamma functions that only depends on the scaling dimensions, delta I, and the space-time dimension d. Okay? So there is a limit of this type between the OP coefficient and the local cubic coupling with some explicit function here that can be computed analytically. I guess this is obvious if you know ADS-CFT. I mean, it's clear from what I'm saying. But if you don't, yeah, just take it as a particular case of this general formula that can be derived. So there is this relation. The important thing I want to emphasize in this relation is that if you study these gamma functions at large arguments, okay, some Stirling approximation, you see that this becomes some function of the ratios, but then there is some exponential dependence, okay? So there is some factor which is bigger than 1 in general, which is raised to the power delta 1. So this factor grows exponentially in this limit, in this flat space limit where all dimensions are going to infinity, okay? So we're trying to extract flat space physics from this box of size r, and this limit corresponds to all dimensions going to infinity, as we saw. And what we see then is that in order to get a finite cubic coupling in flat space-time, we need this OP coefficient to decrease exponentially when we take the flat space limit, okay? And in fact, the exponential decay is entirely fixed by this formula, so we know the precise coefficient in the exponential decay, okay? So keep that in mind for the plots I will show in a few minutes. Okay, I will not have time to discuss this resonance. We can discuss afterwards. Sorry. So let's then. Yeah. Any question about the logic? So this is the generic logic. You want to study a quantum field theory, you put it in ADS, in this very nice symmetric box. That tells you that there are these observables that live at the boundary, obey all the properties of a conformal field theory. Now we're just going to apply the machinery of the conformal bootstrap to this set of observables and find information about quantum field theory, massive quantum field theories. Okay? This is the logic. So now I want to do an explicit calculation, also involving this numerical bootstrap, to see what we can learn from this method, what we can learn about quantum field theory, massive quantum field theory. Any question?
So, from the boundary point of view, these observables are also operators on the boundary, and they also should obey boundary bootstrap.
They obey, exactly, they obey d-dimensional conformal bootstrap equations, yeah. The only axiom, the only condition that is missing is the existence of the stress tensor, but all this OPE associativity logic, these crossing equations that I wrote, they still hold for this set of observables.
So this is different from the bootstrap that you impose in the bulk?
In the bulk? Yeah, I'm not doing bulk bootstrap because the bulk theory is not necessarily conformal, so it's very hard to do directly bootstrap for correlation functions, or for local correlation function in non-conformal theory, because, I don't know, even the 3-point function depends now on ratios of distances, and, sorry, depends on distances. Even the 2-point function is very non-trivial. It's, right? Depends on the distances in a non-trivial way in a massive theory. So it's hard. Maybe it's possible, that's another direction, but I don't know how to do it. Okay, so let's do some concrete question. So let me study two-dimensional quantum field theory. And what I will ask is the following question. I will impose that the energy spectrum is of this form. So I have the vacuum, I have one stable particle of mass m1, then the mass spectrum. Then I have 2 m1, and so I have a continuum. Okay, so this is in flat space. Okay, I'm first stating the problem in flat space, and then we'll translate it to ADS. So this is the spectrum, and I will also allow another particle here of mass m2, which is stable. Okay, it's below the 2-particle threshold. And this theory, in principle, could have a coupling between the lightest particle, 1, 1, 1, 1, okay? But this one I will set to 0, okay? So imagine that this cubic coupling is 0 because there's some Z2 symmetry. The first particle is Z2 odd or something. And then I will allow a coupling 1, 1, 2, okay? So G1, 1, 2 is different from 0. And in fact, my question is going to be, what is the maximum possible value of this coupling consistent with this mass spectrum? Okay? So max of G112 given max given mass spectrum. Okay. So why do I ask this question? Well, you will see that it's a very good question for the conformal bootstrap, for this logic. But why do we expect to have a finite answer to this question? So the point is that if you think of this particle M1, okay, so you M1, if this coupling is non-zero, then the particle 1 can exchange a particle 2, a diagram like that, because this coupling exists. And this exchange of this particle 2 generates an attractive force between these two particles. So if this force is too strong, we expect that two particle states of M1 will want to form bound states. Okay? So we expect that if this coupling is too strong, we want to form bound states, but that is forbidden by our mass spectrum condition. The only state below threshold is M1 and M2. So there should be a maximum value, okay? So the question is, can we draw a picture like that, that if we draw G112, and as a function of M2 over M1, for example, this can vary, let's say, from 2 all the way up to threshold, let's say, up to 0. Is there some line that we can draw here where this region becomes excluded and this region is allowed? Is there such a line? Can we look for such a line? Is the question clear?
Just one clarification. Is the mass spectrum something you have stipulated, or is it something you have derived from somewhere else?
Can you repeat the question?
Is the mass spectrum something you have stipulated, or is it...
I'm stipulating, yes. It's my choice. This mass spectrum is my choice, yes. I'm giving the mass spectrum, say, with this mass spectrum, make the cubic coupling as large as possible. That's the question. But you see, this would be a good way to approach it. You know that the theory only has 2 stable particles, for example. That's something more or less easy to see from the lattice, how many stable particles you have below threshold. You have it as 2. Okay, now let's try to see, is it very strongly coupled? Should we try to maximize some coupling? Maybe we can find a theory at the boundary with these kind of questions. Okay, so the logic, then, we take this question and we translate it to our box. We go to ADS. Okay, so we put this 2D quantum field theory in ADS2. Okay, so that leads to a conformal theory on the boundary in 1 dimension. Okay, so then what I do, I look at the observable, which is, let's say, the 4-point function of this operator of dimension delta 1 dual to this mass M1. Well, let's be faster. So now it's just a line. So I can just choose to put the operators at 0, Z, 1, and infinity. Okay. Just I can use conformal symmetry to fix 3 points, and another way of writing the cross ratios. And so this is some function of Z. And now we can try to apply the same type of bootstrap logic to this function. So in particular, because it's always the same operator, you see Z going to 0 is the same as Z going to 1. So there is a symmetry of this type. And of course, there's also OPE, a consistent OPE. So that's the important part. So now in the OPE, if you take O1 times O2, well, you will have the identity, which would be the analog of here, the vacuum. Then, in principle, you would also have O1, but that we are forbidding, okay? So lambda 1, 1, 1 we set to 0 is the analog of this condition that we set G to 0. Then we have lambda 1, 1, 2, O2. That we don't set to 0. It's important. So what we'll do is to maximize this coupling, right? It's the analog of maximizing the cubic coupling is to maximize the OP coefficient. And then there will be more operators, lambda 1, 1 delta, O delta, where here the scaling dimension must be bigger, greater or equal than 2 delta 1. That's this continuum will be whatever. It will become discrete in ADS, but doesn't matter. What matters is that it only starts at 2 delta 1. Okay? So we impose this spectrum condition. We also have crossing symmetry. Here it's even simpler. Okay, I could give you more equations, but I think it will be a repetition, okay? Is the logic clear? It's even simpler. Instead of having 2 cross ratios U and V, you only have 1 because it's CFT 1 dimensions, only have Z, but I could expand in conformal blocks, then impose that, and then apply linear functionals given this spectrum condition. It's slightly different to problem. It's a small variation of what we did before. Before, we were just trying to exclude assumptions onto spectrum, allowed, disallowed. Here, instead of doing that, is like given a spectrum, we can maximize an OP coefficient. It's a small variation, but it's still a linear programming problem. So the methods still work. Okay? So I think that's sufficient to show you results. Yeah, so we also had before, so what we impose as before, we impose derivatives of the crossing equation, okay? We impose derivatives of the crossing equation at the symmetric point, which in this case is equals a half between 0 and 1, okay? So we impose, let's say, I don't know, I can put here a of z minus a of 1 minus z. Okay? Instead of imposing that everywhere, we impose these derivatives, and we impose these a finite number, okay, from 0, 1, all the way up some capital N. So there's a truncation as before. So N is this parameter, how many equations we impose. So does this work now? Just turn it on. Any question about the logic? Oops. Good.
Sorry, you excluded O1 just because you want to be more generic and get it as a limit of O2 equal O1, or is there something more fundamental?
No, it's just a choice. You see here, so you mean why do I exclude this one? It's just for simplicity. So it's like here. So here I wanted to have some parameter to vary M2 over M1. So, and for simplicity, I only allow like one pole, okay? So in the scattering amplitude, in practice what I mean is that in the scattering amplitude of 4 ones, okay, in this scattering amplitude, there's only one pole when this total center of mass energy, like S, the Mandelstam variable, is equal to M2 square, right, with G112 square. I could also allow another pole, but for simplicity, I removed it. Okay, so what are the results? Good. Yeah, so I think we know all the variables in this plot. So this plot, you see, n is the truncation level, so this is numerics. So we want n equals infinity, but we can only do finite, so we did 40, 60, up to 200. We impose this equation with 200 derivatives, and under that condition, we maximize the cubic coupling, okay? So it's a log plot of the OP coefficient, lambda 112. And you see these curves as a function of delta 1. And we keep the ratio fixed, okay? That's also important. So when you do these plots, you want a given theory in flat space. So a given theory in flat space is characterized by a mass ratio. Of course, the mass scale doesn't matter, it's a choice of units, but the ratio between M2 and M1 is a different theory, okay? So what we do is to approach that theory, we fix the ratio, delta 2 over delta 1, in this case 1.2, sorry. And then we vary delta 1. So what do we want? We want n going to infinity and delta 1 going to infinity. So we want n going to infinity because we want to get all possible constraints, the strongest possible pull, recall, from the bootstrap. And then we want the flat space limit delta I going to infinity, okay? So what do you see on this curve? You see that the curves indeed decay. As you increase n, the bound gets stronger and stronger. That makes sense. I'm imposing more constraints, so it's harder to make lambda big. And then there's an n equal infinity curve in orange, which, of course, was not done at n equals infinity. It's an extrapolation, okay? So what we do, we plot the points as a function of 1 over n, and we do a polynomial extrapolation in 1 over n. I think this one is like 8 degree or something. Okay? That can be dangerous, but in this case it works marvelously, so it just works. You see that the dashed black line is the exponential decay predicted by the formula erased. Okay? So I told you that in the flat space limit, when delta 1 gets large, lambda has to decay exponentially to get a finite cubic coupling. Okay? And that's precisely, so the black dashed line has a slope which is analytic, is not fitted. The black line, I'm only fitting the, how do you say, the shift, like the constant. I'm not fitting the slope. The slope comes from the analytics. Okay? Is it clear how happy I was when I saw this plot? It's quite remarkable that the slope matches. These are numerical results. The dots, the blue dots are numerical results. The orange dots are extrapolated numerical results to large n. And the dashed black curve are analytic result. The analytic slope with a constant which is fitted to that orange curve. Yeah. Okay? So then, yeah, this is the nicest plot. Balt did this. Okay, so this is the two extrapolations. So now we are in this, we have an extra axis. We can also vary the ratio, delta 2 over delta 1. We have these points. So n goes to infinity, we go down from the points to the orange curves. And then once we are in the orange curves, we go to large delta to infinity. And so the red dots are the actual extrapolation to flat space. Can you understand this picture? Okay, so each one, there is 3 of these like towers. Each one of them is this curve. Okay, so I'm plotting 3 of these curves in this 3D plot, and yeah, here I'm normalizing. Okay, here instead of plotting lambda, I plot g. So I normalize using the analytic factors. So after extrapolating, it should be constant. So you see that the orange lines are horizontal. And then I just extrapolate these horizontal lines to infinity, and I get the red dots. Any question about this? Yes.
This black line is giving you the limit, that curve, that below it it's allowed and above it it's allowed.
Exactly. So the black line is what I tried to draw here, but since I was ignorant, I draw something stupid, but now that line is something like that. It diverges and it comes back like that. And this point where it diverges is square root 2, I think. That's what the numerics give you. And everything that is above this line is excluded and below it's allowed.
Did you say why it diverges?
I will explain either today or tomorrow. It's not obvious at all. It's a surprise from the numerics at this level.
And you know from the numerics that it diverges? How do you know it from the numerics?
No, it's because then I will explain how to compute the black curve analytically. First we were surprised by this beauty, and then we understood how to do it analytically, but that's next lecture, or maybe in a few minutes. Okay, so this is the extrapolation to flat space, and okay, it's the curve I was trying to plot there. Okay, mine is more similar. If you put it in a square, never mind. It's clear? Yeah, don't pay too much attention at the blue curve. The blue curve is an analytic curve that I will explain afterwards. What matters is the red dots, okay? The red dots are the ones that are actually computed using these numerics and extrapolation.
So is this thing symmetric on the, like if we exchange M1 and M2, this is obviously, I think it should be symmetric, right? So if we do this on one side of it?
Why do you say that? I think it's different, because M1 is the external particle I'm analyzing, and M2 it's the pole inside. It's a different problem. The symmetry that you see there, it's a slightly different symmetry. It will be obvious after tomorrow.
Also another question. Suppose we choose a mass spectrum in which all the masses are zero, so that the boundary, so that the bulk QFT is also a conformal field theory. So, does bootstrapping on the boundary give any new information in addition to what bootstrapping in the bulk would give you, or is it?
That's a very good question. Good. So yeah, here I only talked about massive theories in the gap theories in the bulk. If it's conformal, then it does not make sense to take this limit of large dimensions because, well, masses are zero. That's one way of saying it. But the other way of saying is that you have a box. If you have massless particles, the first states will have an energy of the size 1 over the size of the box. So delta will be order 1. So, but the best answer is the following. So if you do conformal field theory in ADS, since ADS is just a Weyl transformation of half of flat space, right? In Poincaré coordinates is very obvious, right? It's just z bigger than 0. So this is equivalent to doing boundary conformal field theory. So what you will be studying is conformal field theory in the presence of a boundary. And in that case, everything that I said about boundary operators and their convergent OPE and bulk operators expanded at the boundary, it's all known very well in boundary conformal field theory. It's just boundary operators and boundary OPE. And so if you do that, you will just be studying boundary conformal field theory. It's a bit more than bulk conformal field theory because there's more data. There's data about the boundary operators. But I think it would also be very interesting to study an RG flow between two non-trivial CFTs. Then going to ADS is better than just doing boundary conformal field theory, because if you do an RG flow in the presence of the boundary, okay, in the UV you can have some boundary conformal field theory, in the IR you have another boundary conformal field theory, but along the flow you have less symmetry. While if you do it in ADS, the two endpoints are equivalent, but you actually preserve the full conformal symmetry along the flow. So it should be interesting to study that, but we haven't done it.
Sorry, I'm always a bit confused with ADS2 because it has two boundaries, right? So
depends how you see it. In Euclidean, actually, I'm doing Euclidean, so no.
okay.
So it's the Poincaré disk. It's literally the Poincaré disk. Okay, and I wrote some formula there. That's the analytics expression for the blue curve. We should be able to derive it either today or tomorrow. And this is something I did not explain. It's the phase shift. Okay. Any question? If there's no question, I'll change topic now. Try to explain how to derive that curve analytically. Sorry. So one comment. We also tried to do, you see, the logic is valid in any space-time dimension, right? So why did we do 2D quantum field theories? Because technically it's much simpler. Essentially it's the fact that you only have one cross ratio, so you can take many, many derivatives. If you have two cross ratios, so here we were going up to 200 and sometimes 300 derivatives. If you have two cross ratios like you have in higher dimensions, then you have to take two derivatives in two variables, so the most we can do is to go up to 30 or something, 30 or 40 I think. And that's not sufficient. So what we observed is that if we ask an analog question in higher dimensions, for example in a 3D quantum field theory, which corresponds to a 2D conformal field theory on the boundary, we find that the finite n results are still very far from the n equal infinity results. So the extrapolation to n equal infinity just does not work, and we cannot reproduce the scaling we expect from flat space, okay? So, well, Not sure. Maybe some better idea to how to bootstrap directly in this flat space limit or something, but so far we were not successful. Okay. Okay, so this is the end, second part. So now we start the third part. So third part is the same logic, same philosophy, bootstrap. But now we're going to choose different observables and therefore different consistency conditions. So what we're going to do is to do directly an S matrix bootstrap. Okay? So the observable that we are going to study is the S matrix, and we're going to impose consistency condition directly on the S matrix and see where that leads us. Okay? So I will start in 2D, and tomorrow I'll tell you about 4D. So let's be concrete. So let's consider the scattering process that we were analyzing before. So particle 1, the lightest particle, 2 to 2 scattering. So if you are in 2 dimensions, both energy and momentum are conserved, and since you only have 2 components in the momenta, essentially the momenta can only be permuted. Okay, so in practice, what that means is that from the 3 Mendelssohn invariants, so S P1 plus P2 square, and T and U, the analogous things, okay, you can always set U to 0, and you just have that, and then you always have S plus T plus U equals 4 M1 square, right? But since U is 0, because in 2 dimensions you have this extra condition from the finite space-time, this is just a function of S. Another way of saying is that there's no scattering angle, right? So the S matrix is just a function of the energy. And moreover, you have crossing symmetry. So if you permute S and T, just tells you that, so let me write it here. Crossing symmetry just tells you that S of S is equal to S of 4m1 square minus S. Okay, permuting S and T. So now we're going to do as before. So we will think of this process in a theory. Yeah, let's keep the same. I shouldn't have erased it. Let's keep the same spectrum. So there is this M1, there's an M2, 2M1, and a continuum. Okay, this mass spectrum. So in particular, this will contain a pole in S when S is equal to M2 squared, and the residue will be this coupling, G112 square. Okay, I'm defining the cubic coupling to be this residue. So, okay, so this is the observable. Now what are the consistency conditions? You already have one, this symmetry. The other consistency condition is analyticity. So it's the analytic behavior of this function in the S-plane. So let me try to draw that. In the S-plane, how does this function behave? So let me draw it like that. What are the singularities of this S-matrix element? So you can have a cut that starts at 4m1 square, right? That's the 2-particle cut when the energy is above the 2-particle threshold. Then you have this symmetry, so that means that you also have a cut the t cut starting from 0 to minus infinity. Okay, so there is a symmetry around, crossing symmetry is a symmetry, a reflection symmetry around this point, 2m squared. Okay, and now you can have poles associated to these bound states, okay, to stable particles below threshold. So we are not allowing m1, so we only have a pole here at m2 square, which corresponds to the S-channel process. 1, 1, 1, 1 goes to 2. So when you have exactly S is exactly equal to the mass 2 square, you have a pole. And you also have a pole here, which is a T-pole. So it's at 4m1 square minus m2 square, which corresponds to when T goes on shell like that. Okay? So when T is equal to m2 square. Okay? And this is an assumption. Essentially, analyticity is some mathematical way of imposing causality. So, yeah, essentially, it's hard to prove rigorously, but it's clear that if you have singularities somewhere here lost in the complex plane, then you would be scattering, and then you use this S matrix to describe some scattering process. You prepare some wave packets, and the final result of the scattering can reach you before you actually send the wave packets. Okay? So it's this notion of causality that scattering happens after it happens that imposes that you cannot have any other singularities in this plane. Okay? Okay, these are two consistency conditions, and the last one is unitarity, which in this language of this 2 to 2S matrix is extremely simple. It's just the fact that if you take your S matrix element and you compute this norm square, that's a probability of starting from this two-particle state and ending in the same two-particle state, so that has to be less than 1 for all S physical, okay? So above for m1 square, which is the minimal energy you can have for this process to occur, right? It's the minimal energy that you can have to have two m1 particles. Sometimes you can write here plus I0, right? Because this is the physical values of the S matrix. The values that give probabilities are values measured here just above the cut. Okay? Those are the physical values of the S matrix. It's dangerous. You asking questions about S matrix, it's not going to be easy. Good. Yes.
Can I see singularities elsewhere?
That's crucial. So this is simple because I'm staying in this first physical sheet. I'm not entering the cut. If I enter the cut, all hell breaks loose. It's like anything can happen. Use extreme complication. Even in perturbation theory, we know that once you enter the cuts, you can have lots of singularities. As you go higher and higher in loops, more things appear, okay? So here it's crucial for us. We will always stay here and just treat these discontinuities, just parameterize the discontinuities without ever asking what's happening to the analytic continuation if you actually go inside. Yes, the philosophy is that, yeah. Okay, let's see. Did I say everything I want to say? Yes. Okay. So the problem is clear. So now I have this function with these analytic properties, with this unitarity condition, and the question I want to ask is, what is the maximum value of the residue, max of G112 square, given this analytic structure, so this spectrum and these symmetries, okay? So that's the question. It's a very sharp mathematical question. Can I find a function with these properties that has a residue arbitrarily large? You can already see that it should be hard, right? Because if you make here a residue very large, well, the function will be very large, but here it cannot be large because it's bounded. Okay, so let's solve this problem. So this problem was solved, I think, in 1972, I think, by Michael Kreutz. Unfortunately, his paper had 0 citations, and it was very hard to find. We had to find the solution before, but his paper is 2 pages long, and it's very nice to read. So let me try to explain you how to find the solution to this problem. So, so the logic is very simple, actually. It's very clean, and then it generalizes very nicely. So what do? You take this function, and okay, you don't even have to do that, but just to be more pedagogical, let's map this to the unit disk, okay? So we have these cuts, so this is a boundary of the function. So let's map it to the unit disk. So there's a map, let's say some z coordinate, where I take this analytic domain. So there is this cut here, like above the cut and below the cut. Let's say this is A and this is B, okay? So this point here, let's say this is the unit disk, so this is z equal 1. This point here corresponds to s equals 4m squared, m1 squared. And then this top boundary is A, this lower boundary is B, okay? So this point here corresponds to s equals infinity. And then here, actually, since you have so much symmetry, you have this crossing symmetry. So this line, you can, if you know the arithmetic on this side, you know on this side by crossing symmetry. And in particular, the value of the S matrix here is the same as the value of the S matrix there, right? It's glued by that. Okay, so what I do an analytic map that maps that to here, some region here. Okay, so let's say this is C and D. It's glued together because crossing symmetry then says that the S matrix takes the same values there. So this is C and D. And then inside this region now, so A, C, D, B, okay, inside this region, I only have one pole at m2 square, and I can do this transformation to a variable z where that pole is exactly at 0. So this is S equals m2 square. I can write the equation if you want. I have it there, but it really doesn't help more than what I'm drawing. Okay? There is a function S of z that performs this transformation for you, maps this part to the interior of this unit disk. Okay? So now, in this variable, we have a problem which is S of z. It's analytic everywhere, up to a pole at the origin, whose residue is basically, there's some Jacobian, but it's proportional to G112 squared. And what we know about this function is that S of z at the boundary of the disk is bounded by 1, okay, when z is equal to 1. Okay? So now it looks simpler, right? Now a mathematician would like this problem. That problem looks a bit ugly, but this problem, I think a mathematician would tell you the answer immediately. Okay? Now you have what is the function, what's the maximum value of the residue given that the modulus is bounded by 1 at the boundary of the unit disk. Okay? And in this formulation, the answer is that, well, let me explain the answer. I think I don't have time for more, so let me explain the answer. So how to solve this problem? So what you do, it's very simple. You just define a function, let's say age of z, to be z times s of z. Okay, define this function. Then with this definition, now the maximum value of G112 square is just the maximum value of h of 0, right? Because I multiplied by z. So now the function h is analytic everywhere. And the the unitarity condition, is still the same. It's still the same because I multiplied by z, but z is just a phase at the boundary. Okay? So now you have an analytic function inside the unit disk bounded by 1, whose modulus is bounded by 1 at the boundary, and you want to maximize its value at the center. Okay? So this is like the maximum modulus principle. So the maximum of the modulus of an analytic function is always at the boundary of the domain. It cannot be inside. So the conclusion is that the best you can do, so the optimal solution, is to set h of z equal to 1. Okay? And then h of 0 is 1. That's the best you can do. You just set the function to be constant, and that's the maximum value that it can have at the origin with this boundary condition. Okay? Is this clear? So this is max modulus principle or something. You can read in Wikipedia. Okay? So this would tell you that this is 1, and okay, the way I did it looks trivial, but that's because I forgot here there's some Jacobian that depends on the ratio m2 over m1, and that's the plot that you saw. This analytic curve just comes purely from this Jacobian. When you map from S to this z-plane, in this z-plane, the maximum residue is 1, but when you map back, there's some Jacobian, and the maximum residue is that function that you saw before. Okay, and you see here the logic is very interesting, and it's very simple, and you can do now many theories. Because the trick is always you guess, okay? You guess an answer with the right poles, and then you take the ratio to the S matrix. If your answer saturates unitarity, okay, let me present this answer in a slightly different way, so that you see how easy it is to generalize. To have more poles, for example. Let's see if I can, yeah. So let me write it. It's the same argument, but slightly different. Write an S guess like that. S. So once you understand the logic, then this S guess is very simple to understand what I'm doing. Okay, so it's a plus, it's 2 square roots plus divided by minus, the same square roots. Okay, so why do I write this as the S guess? Okay, so what are the properties that are important? Why is this guess good? Okay, this S is good because, first of all, it is a pure phase on the cut, okay? Here, on A, it is a pure phase. It's easy to see that, so this part is some positive real number, so this square root is a real number. But here, when S is bigger than 4m squared, this is negative, so this is purely imaginary, okay? So here, this is just a number divided by the complex conjugate, or maybe there's a minus sign, okay? So it's a pure phase. So properties. It's a pure phase, S guess equal to 1 for S bigger than 4m squared and real, okay? The other property is that indeed it has poles when S, so poles when S is equal to m2 squared, okay? right? S is equal to M2 squared. This just cancels, so you have a pole. It also has the crossed pole, okay? It's also crossing symmetric. S of S is equal to S of 4M squared minus S, okay? So it has these three properties. S guess, sorry. S guess. Once you have an S guess with this type of properties, now you take the ratio, the S divided by S guess. Okay, let's say this is our function h of S. Now this function doesn't have poles anywhere. It's also bounded by, modulus is bounded by 1 at all the boundaries. Okay, so the biggest this function can be at any point in the interior is 1. Okay, it's exactly the same argument. So what we'll see is that now if you want more poles, you just multiply several of these S guesses, because each one is a phase. So if you multiply, they are still a phase here, and you can just put as many poles as you want. And the optimal solution is just a product of factors like that. Okay, and these factors are known in some integrability literature as CDD factor. Okay. If I have time tomorrow, I will explain a bit more. Okay. So yeah, so tomorrow we will finish this general story in 2 dimensions, how you can do everything analytically. But then to go to higher dimensions, I don't know how to do it analytically. It's probably not possible. So we will have to do numerics. So we will first redo this problem numerically in 2 dimensions, and then we will, from that, learn how to go to higher dimensions and do numerics directly for the S-matrix bootstrap. Okay? But so the conclusion from today is that we have 2 approaches for bootstrapping quantum field theory. One is putting it in ADS and just using the standard conformal bootstrap. Another one is to try to directly bootstrap this flat space observables like the S-matrix, and they match. Okay? They match exactly in the cases where we can do both things to the end. Okay? Thank you.
Thanks a lot. Very nice lectures. So, immediate questions still before lunch? We had already many questions. So, okay. Thanks a lot. So then we reconvene at 2:30.